Imagine a universe that lives only on a flat sheet of paper. In Edwin Abbott's novel Flatland, shapes are people. A triangle, a square, a circle. They know left and right, forward and back. They have no word for up. Their whole world is the plane they stand on. Every door is a gap in a line. Every shadow is a shorter segment. There is no sky above them because above is not a direction they can name. When a sphere from our three-dimensional space visits Flatland, the flat beings never see a ball. They see a point appear, grow into a circle, swell, shrink, and vanish. That circle is only a slice, a cross-section of a higher form pressing through their world. The sphere may be smooth and complete in 3 dimensions, yet Flatland receives only a changing disk of contact. That is the usual story. How the lower dimension meets the higher one. It is a beautiful story, and it is still only half of the geometry. Today we reverse the camera. We ask a quieter, sharper question. How does a 3-dimensional observer actually look at a 2-dimensional object? What does projective geometry do to a square and a circle when the eye is free to move above the plane? We will walk 3 visual states with real numbers. God eye view at tilt 0. Oblique foreshortening with cosine. Edge on vanish at 90 degrees. Then we will use Flatland as a clean analogy for higher dimensions, and for the way our own eyes already project the world. Before the camera tilts, fix one definition. Call the plane of Flatland the paper. Call the direction straight out of the paper the normal. The tilt angle, theta, is the angle between the line of sight and that normal. When theta is 0, you look straight down the normal. When theta rises, you look more and more sideways. When theta reaches 90 degrees, the line of sight lies parallel to the paper. That single number will drive almost every picture we draw. First, the God eye view. Point a camera straight down so the line of sight is perpendicular to Flatland. Call the tilt angle 0. A circle looks circular, a square looks square. Distances measured in the plane match distances measured in the image up to one global scale. True geometry is revealed. Artists call related ideas orthographic or plan view. Engineers draft floor plans in the same spirit. You are not inventing a fantasy camera. You are using the simplest honest projection. But something stranger also happens. In 2 dimensions, a wall is a line that blocks light along the plane. Privacy is absolute for neighbors who share the same world. From above, those walls have no height. Light in the 3rd direction is not blocked. You see rooms, furniture, and the square himself at once, without breaking a single wall. A boundary encloses volume only inside its own dimension. Add a 3rd axis, and the wall has no thickness to stop your gaze. Mathematically, occlusion requires a surface with extent against the ray. A line in a plane does not stop a ray that is not in that plane. Think of a maze drawn in ink. From the side, corridors hide each other. From directly above, the maze is an open diagram. Flatland privacy fails the moment a higher dimensional ray is allowed. That is not magic. It is missing thickness. Second, the oblique view. We rarely look straight down, tilt the line of sight and perspective takes over. The near edge of a flat square stays large. The far edge shrinks toward a vanishing line. The square becomes a trapezoid. A circle becomes an ellipse. Parallel lines that run into the depth of the paper no longer look parallel on the screen. The shape has not changed. Only the projection has. The object is still a square in its own geometry. Your eye is sampling a different set of rays. Here is a small concrete picture. Place a unit square on the table. Keep one edge near you. Raise the far edge an angle only in the sense of the camera, not by bending the square. As theta grows, that far edge occupies fewer degrees of visual angle. The height of the figure on the image plane falls. Corners that were right angles may look acute or obtuse after projection. Children discover this when they draw a tabletop and struggle to make the legs look right. Projective geometry is the adult name for that childhood puzzle. Here is the foreshortening rule in plain words. Take a segment that lies along the direction you are tilting. The length you see is the true length multiplied by the cosine of the tilt angle. Write it once so it sticks. Scene length equals true length times cosine of theta. At 0 degrees, cosine is 1, so the image length equals the true length. Nothing is crushed. The diagram is honest. At 30 degrees, cosine is about 0.87, so the segment looks a little shorter. You still recognize the figure, but vertical extents have already begun to compress. At 45 degrees, cosine is about 0.71, so roughly 30% of the height is gone from the image. At 60 degrees, cosine is 1/2, so vertical extents look half as tall. The square is clearly squashed. The circle is a wide ellipse. At 80 degrees, cosine is only about 0.17, and the figure is almost crushed. At 85 degrees, the cosine is near 0.09. Watch the number fall as the angle rises. That falling cosine is the mechanism behind foreshortening. It is not a filter. It is not a style choice. It is trigonometry applied to the component of a length that faces the eye. You can check the rule with a card. Hold a playing card flat, face toward you, at arm's length. That is near zero tilt for the face normal. Now slowly tip the top edge away until the card is almost edge on. The face height in your vision shrinks roughly like the cosine of the tip. The width changes less if you tip only in one axis. Artists practice this until the hand knows the curve. We are naming the curve. Third, the edge on limit. Raise the tilt all the way toward 90 degrees. Cosine of 90 degrees is exactly 0. Every height in the plane collapses in the image. A perfect mathematical plane has no thickness. Viewed exactly edge on, it contributes no area facing the eye. It can vanish into a line or into nothing you can resolve. Paper in our world still has atoms. A true plane does not. That is the vanishing plane. The cross-section of sight with a set of 0 thickness has measure 0 in our view. In measure theory language, a set can be non-empty and still contribute nothing to area on the image. Flatland idealized is such a set when you look along it. Real ink has width. Real paper has fibers. The idealization is still useful because it marks the limit of the cosine story. Foreshortening does not stop at 80 degrees. It continues until the facing component is gone. There is a twin statement for length. A thin rod pointed straight at your eye can look like a point. A disc seen edge on can look like a line segment. Orientation relative to the line of sight decides whether extent survives in the image. Flatland is the extreme case of a whole world that has extent in only 2 directions. Tip your gaze into the missing direction, and the world thins to nothing. Fourth, a paradox about us. We live in 3 dimensions, but the retina is a curved sheet of sensors. When light enters the eye, a 3-dimensional scene is projected onto a 2-dimensional surface. The lens focuses rays. Photoreceptors sample a field of angles, not a solid volume. The brain then rebuilds depth using 2 eyes, shadows, motion parallax, and prior knowledge of object sizes. In that sense, we are 3-dimensional beings who sample the world through a 2-dimensional measurement. When we look at a drawing, we project a plane onto a plane. Double projection. First, the artist flattened a scene or invented a plane figure. Then your eye flattens that plane again onto the retina. That is why screens feel native. A glowing rectangle is already almost the shape of the measurement surface. A flatlander would understand the surface of the retina as a kind of home. The flatlander would still be lost in the reconstruction our cortex performs every second. The silent inference that turns an ellipse into a coin tilted in space. Stereopsis helps, but it is not the whole story. Close one eye and depth does not vanish. Familiar size, occlusion, texture gradient, and perspective still work. Cinema relies on that. One camera, one image plane, and yet a city can feel deep. Flatland gives language for the gap between the measurement and the world. The gap is not a failure. It is the price of a sensor that is a sheet. Fifth, the 4-dimensional mirror. Use Flatland as analogy, not decoration. Just as we look into a closed square house from above, a 4-dimensional observer could look along a direction perpendicular to our entire space. Walls, vaults, and even skin would not hide interiors the way they hide them from neighbors in 3 dimensions. A sealed room is sealed only against paths that stay in 3 dimensions. An extra axis opens a new family of rays. The same projection ideas scale. Foreshortening, vanishing, and enclosure are not special effects. They are geometry. If you rotate an object in a higher dimension, its shadow in our space can stretch, reverse, flatten, and disappear for the same cosine reasons, only with more axes. A tesseract, drawn as a cube within a cube with connecting edges, is only one popular shadow. Other rotations produce other shadows. None of them is the full four-dimensional object, just as the growing circle was never the full sphere. Think again about privacy. In Flatland, a closed square believes its interior is secret. From the third dimension, the secret is public. In our world, a closed vault believes its interior is secret. From a fourth spatial direction, if such a direction existed as a free axis of motion, the analogy says the secret would be public in the same structural way. We do not claim to live in that world. We claim the logic of enclosure is dimensional. Boundaries bind what they can face. You can push the analogy carefully into science fiction and still stay honest. A four-dimensional surgeon, in the old thought experiment, could reach an organ without cutting the skin the way we cut. By moving through a direction, we cannot block with a three-dimensional surface alone. Whether physics allows such motion is a separate question. The geometric claim is narrower. Surfaces that separate regions in three dimensions need not separate them once an extra independent direction is available. Sixth, a short workshop with numbers. Suppose a segment of true length 10 units lies along the tilt direction. At 0 degrees, the scene length is 10. At 30 degrees, the scene length is about 8.7. At 60 degrees, the scene length is 5. At 80 degrees, the scene length is about 1.7. At 90 degrees, the scene length is 0. Plot those 5 points. The curve is the cosine curve restricted to a quarter turn. Every crushed rectangle you have ever seen in a diagram is a sample from that curve. Now place a circle of radius 1 in the plane. Under a simple orthographic tilt about one axis, the image becomes an ellipse with semi-axes 1 and cosine of theta. Area on the image scales by the absolute value of cosine of theta. At 60 degrees, the imaged area is half. At 0, it is full. At 90, it is gone. Area is not a mystical invariant under projection. Orientation relative to the eye decides how much area survives. If you add true perspective with a finite eye distance, the story gains vanishing points and depth scale, but the qualitative crush remains. Far features shrink. Near features dominate. The cosine rule is the clean orthographic core. Perspective is the refinement when rays are not parallel. Both are projections. Both discard information. Both can be inverted only with extra assumptions, which is why reverse engineering a three-dimensional scene from one photo is an art as much as a calculation. Seventh, return to Abbott for a moment of story, then leave the story in its proper place. A square meets the sphere and is lifted out of the plane. Terror, revelation, and the sermon about higher worlds follow. That narrative made Flatland famous. Our job here is slightly different. We keep the beings of Flatland as a measuring stick for projection, not as characters we must follow through every chapter. The geometry should still work if you never liked the novel. A plane, an eye, and a tilt angle are enough. Close with useful humility. We cannot visualize a fourth spatial axis the way we visualize height. Our nervous system is built for 3 coordinates of free motion and for images on 2-dimensional sheets. But we can still calculate. Projection matrices, homogeneous coordinates, and careful diagrams let us reason about views we cannot inhabit. Linear algebra does not require your imagination to finish the picture before the matrix multiplies. The next time you look at a figure on paper, notice what you are doing. You are the higher dimensional observer of that plane. You hold the God eye when you look straight down on a map. You hold the oblique crush with its falling cosine when you tip a book. You hold the edge on vanish when a card becomes a line. All of that arrives with a tilt of the head. No portal is required. And when someone says a higher dimension is unthinkable, answer with the smaller truth first. Even 3 dimensions are only partly thought. We think them through projections, shadows, slices, and symbols. Flatland is a mirror held up to that habit. The lower world teaches the method. The higher world inherits the same method with more axes. Mathematics is how we step outside the paper without leaving the room. Keep the cosine in your pocket. Keep the God eye, the oblique view, and the vanishing plane as 3 buttons you can press on any diagram. With those 3, Flatland stops being only a Victorian fable. It becomes a portable laboratory for seeing.